Welcome to Daddy's Podcast.
This is the Redefining Plastics Podcast. Welcome to the Redefining Plastics Podcast. My name's Justin Riney. Again, we have Samantha Ryan as the co-host. We got an interesting one today. It's going to be a fun conversation, I think. A little bit outside of my wheelhouse. We're going to talk compostables today. And we've got Leah Ford from CJ Biomaterials. I will say, I used to buy from CJ Biomaterials, and it's still outside of my wheelhouse. I still don't quite understand exactly how all of it works, but I appreciate you being on. And I want to give the audience a little bit of a background on who you are and who CJ is.
Sure. So Leah Ford, I'm the marketing director here at CJ Biomaterials. So CJ Biomaterials is a division of the company CJ Cheoljadang, which is a large South Korean lifestyle company, and they have verticals in entertainment, logistics, food, and biology, which is where the biomaterials business sits. So the biomaterials business, we opened up a manufacturing plant in 2022 and have been putting out PHA polymers to the market since then. And for myself, I've been in the biopolymers industry for almost 20 years now, actually.
20 years.
Before I joined CJ about a year ago, I spent about 19 years working for NatureWorks. So very much on the PLA side of the business. So my whole career is here.
Yeah.
Yes.
Yeah. So my background's obviously in packaging. So I do have quite a bit of experience in biopolymers. So I want to make sure that we differentiate between the biopolymers that you're talking about and bio-based materials that are being used to make traditional polymers. So you're taking the fossil fuel derived in fossil fuel is a misnomer. Shouldn't say that, but everybody says fossil fuel. So I'm going to run with it. So the fossil fuel derived feedstocks, you take those out and you use cooking oil or technical corn oil or something else to make the same polymers. That's not what we're talking about. We're talking about completely different types of material made completely from bio, and then they're compostable, either industrial or home compost. So I just want to make sure that the audience understands we're not talking about bio-based polypropylene or something like that. We're talking PHA, PLA. What else is in there? Is that pretty much what you're focused on, or is there?
There are some others. There are actually some other what you would consider biodegradable polymers that are made from actually fossil-based precursors, to use the language. So your PBAT, PBS, these materials do have a bio route, but they also right now are made with fossil fuel precursors. But they are readily biodegradable, similar to PLA or PHA. So my area of expertise is definitely in the bio-based biodegradable space, which is PLA and PHA, but there are more biodegradable polymers out there, which is actually really great because it gives us more polymers to work with when we're trying to design for compostability, biodegradability, these sorts of things.
Yeah. So you're out there trying to make sure that you're matching up the polymer, in this case, the biopolymer, to the application. So it makes the most sense for whatever the application is. Because I think there are a couple different things that I've always run into when I've been talking to legislators or I'm talking to big brands. And one of the big concerns about PLA, we'll just start there, is the lack of industrial composting. I know it's getting better. It's growing across the U.S., but there are still pockets of the country that don't have that. But I think PHA, just from my personal opinion, is a great solution because you can home compost. Because I'm a big home composter, and if we're taking packaging and it's going to be coming to the home and you're home composting, you just take the whole thing, you take it straight to your compost bin, and you've solved the problem. And I think that's a wonderful solution. So not to say that PLA is necessarily bad if you've got an industrial composting. I'm just a much bigger fan of home composting. That's just kind of where my head's at. But why don't you kind of walk through the differences in the
Yeah, that was going to be where I was going to jump.
What's the difference? What makes one home compostable versus the other? And could you possibly home compost PLA in the right circumstances? I'd love to have that conversation because, like I said, I'm not an expert in this area at all.
It's composting is a super interesting field, right? Because commercial composting, especially, and I'll just mostly speak for the U.S. market because it's different, especially in Europe and other countries. But in the U.S. market, composting as an infrastructure really grew on the back of being able to compost like landscape clippings, right?
Yeah.
And in that process, the reason that they have commercial composting is so that it gets hot enough to be able to kill weeds and seeds, so that when you get to the compost state and you're using it as a soil amendment, you're not proliferating invasive species, right? And as these compost sites grew to start accepting food waste, the high heat temperatures, like the 58 degrees C that you need in a commercial compost environment, it's hot enough that it killed pathogens in meat, dairy, citrus. Like it's needed to be able to create safe compost. And so I think it's important to know that commercial composting is not something that grew because of biopolymers. Biopolymers have designed themselves around commercial composting for food waste, because the value of commercial or of compostable packaging, right, is diverting food waste away from landfill, because the EPA has shared that, 58% of the methane emissions that comes from landfill comes from food degrading. So that commercial composting environment is ideal for the safe composting of all of those food scraps. And you're right, to date, I think the last data point I saw is that only 4% of the food waste generated in the US every year is sent to compost.
Yes.
And so there's a ton of opportunity. So we need commercial composting infrastructure if we are going to be able to tackle food waste. And the rate at which that's been growing is tremendous. You look at a state like California, which has a statewide organics diversion mandate where they have to take the food scraps out of landfills. That spurred a lot of growth and pressure on the commercial composting industry there. In Minnesota, where I am in the Twin Cities, the metro area has had certain carbon reduction targets, and the only way to get there was to start taking food scraps out of landfill. So we've had the proliferation of commercial composting here just to be able to hit those food waste diversion climate targets. And biopolymers have been, if you will, like molding themselves around how this legislation has been going and about what's happening with food waste. So I think that's important context, because sometimes I hear, especially just for PLA, like, well, it needs a special environment. Like food needs a special environment, right?
True.
I would not invite most home composters to be composting meat scraps in their backyard.
I don't. Yeah.
Right. So I think that's important to know that I think there are places and times where home composting and commercial composting need to overlap and be compatible. So with that being said, you're right, especially in areas where commercial composting doesn't have access yet, we're actually seeing a proliferation of different types of levels of composting, even between home and commercial. There's, community composting, small drop-off sites, like community gardens are starting to do composting. So we're seeing like access to being able to compost food scraps grow at a kind of a nice spectrum of levels, from just you at your home to a large, commercial composters serving a municipality. And the certifications that have developed kind of around compostable packaging have similarly molded themselves around these environments. So when, OWS was getting started trying to create lab tests to certify products for compostability, they're like, okay, what does it take to compost banana peel and dairy scraps? Like, how do we create lab conditions that mirror that, so that we know if there's a safe food composting environment, biopolymers will go away too. And that's kind of how those first standards and certifications for how fast you need to biodegrade, disintegrate, and at what temperatures were designed for. They weren't designed around the properties of biopolymers. It was designed around what we need to do to make food safely compost. So I think that's helpful, because I think that's also a different framing than what a lot of people expect when it comes to how we certify. And as home certifications have grown, there's a great home certification from TÜV or TÜV, depending on how you say it, out of
TÜV
Europe.
is usually what I've always said. TÜV Rhineland. It's
Yes,
typically
that's the
what I
one.
say to people.
Exactly. So their certification is based on a standard that was developed in France, right? Where they looked at how do people home compost? What are reasonable home compost conditions here? And other organizations now are working to expand home compost certification and try to develop eventually an international standard for home compostability like we have for commercial compostability. So, because the thing is home compostability is so variable, right? Here in Minnesota, where I am, like composting through the winter is very different than if you are in Arizona or if you're in the Southeast, right? In South Carolina, where it's a lot wetter and warmer because moisture as much as temperature is incredibly important for the composting process. So I think that there's some challenges with designing products meant for the home compost environment because it is so variable and we don't want products to fail in that environment, right? So
There's nothing worse than looking in your compost bin and seeing something that's not composting. Like you accidentally put something in there you shouldn't have. Digging that out of there is not fun.
And
we'll say from personal experience.
Exactly.
Oh
gosh. Especially if you're doing vermiculture and you have to go through the worms, right? Like that's always a special bit of fun.
I'm not good on that. I'm a little squeamish at heart. So that's not it's not typically what I like to do.
We do it when we have to.
Exactly.
Right.
So yeah, I'm a huge proponent of compost. I think composting is one of the easiest things that people can do to lower their carbon footprint. Because you are dead on. The amount of methane that comes out of a landfill because of food waste is massive. It's like 14% of the entire U.S. emissions of methane is food waste.
Higher. It's like a third. Yeah, it's
now
huge.
It is? Well, yeah. Because that was an EPA data point from like 2022.
Okay.
But the big thing that I think a lot of people don't understand is 1/3 of all food produced in the U.S. just gets wasted. So if we don't take care of that in the right way, so not only do you have the carbon emissions for making the food, like growing it, watering it, all that kind of stuff, then you've got the end of life portion of it that's a problem too. And I like the idea of trying to piggyback on a system that's already there. So taking packaging to a system that's already existing makes a ton of sense. And I think we should do more of that. So what do you think the target markets are for you? I know the food packaging makes a lot of sense. Are there any other markets out there that to you make a lot of sense for your types of materials?
Absolutely. Absolutely. For a really nice combination of the amorphous PHA that we make and PLA, you can make really beautiful nonwovens, right? And nonwovens are used in a wide range of hygiene applications, wipes, baby diapers, etc. And what we are sort of just getting to in the biopolymer space is not just what are these good for when you want to compost something, but also what performance properties do they have that are a unique advantage over incumbent materials. Because for the same reason, right, you use polystyrene versus polypropylene versus PET. PLA and PHA have a similar different suite of properties. So where can those be leveraged to its performance advantage, even beyond, the fact that it's bio-based or compostable? And nonwovens is a really interesting space to do that. Because if you make a really nice nonwoven with PHA and PLA, you can get something that's very soft, very similar to your incumbent polypropylene, but you can actually outperform polypropylene in terms of fluid management. So when they're testing these nonwovens for diapers, they call them insults. And so if you insult the nonwoven multiple times, over time, it does a less efficient job of removing moisture away from the skin and dispersing it to the super absorbent polymer beneath.
So we're talking PLA diapers.
You could.
In essence.
Yes. Yeah. So you can create like this the part that touches the skin to be incredibly efficient at taking moisture away, which reduces the incidence of diaper rash and skin irritation. So I like to say that like by the time I am an adult, I would like my PLA PHA adult diaper so that my daughter never has to treat my diaper rash less because that is
I like that.
not cool.
Yeah. So that's one target market you can to the depends people.
Exactly.
Yeah, I think so I want to talk about some of the, we'll call them misconceptions, because I'm sure that's what they are. But this is just what I see. And
Yeah.
I would love you to correct me where I'm wrong. Does that make sense?
Let's
Kind of
do
where
it.
we're going? So I go to Starbucks today here in Charlotte. And I get a coffee, which I don't do. I always take my own, but we'll just say.
Yeah.
It's a PLA lid. What do I do with that? Where does it go? I have no idea what to do because right now in Charlotte, there's no pickup for yard waste. There's no pickup for compostables because I have friends that live in Los Angeles and they've got a bin that's for composting. So they put their stuff in there and compost. So in a place where you don't have those kind of services, what do you do with these materials? Do you send them just
Like
into
I live
the
in
trash?
an apartment. I live in an apartment
That's another
building.
good place.
We don't even have a recycling chute. We
I hate
literally
that.
just, I know, my old building did, and that was the first building I ever lived in that had a
I need to talk
recycling
to the
chute.
management of your facility.
But this recycle, we do separate like cardboard, but I think that's mainly so they don't deal with it in the dumpster. But we only literally just have a trash room with a trash chute. So like even if you recycled,
with the management
you'll have
of
to
your
have management all
complex.
over Tampa because really I've lived in probably 6 different
That's a problem.
complexes and one had a recycling chute in all of them. So I guess that's a good example because here I literally only have a trash chute.
Yeah.
So what do you do if you're in Sam's apartment? What do you do with your PLA lid? I'm just curious.
Can you clarify PLA and then you said
Polylactic acid.
Okay. And then what was the other one? PHA?
Lactic acid, think the sour stuff on your candies.
Okay.
Yeah.
Okay.
Or it's used in yogurt. Your muscles make it when you work out, right? With the lactic, that's,
And then you get to the point where your legs are burning and you can't stand up anymore. It's because you have a buildup of lactic acid.
Okay. I'm familiar now that when you put it that way.
Yeah, I'm not because I'm sedentary. But yeah, I think it's a good question. Like, what do you do if you don't have a ready outlet for an industrial or commercial composting package?
Yeah. Step one, if your building or home or city isn't providing it, is definitely to look for a local community drop-off site because private community drop-off is growing like gangbusters right now. Because the other part of composting to note is that compost is a valuable product in and of itself.
It really is. I bought it before I started doing it myself. It's expensive.
Yes, it is.
It really is.
It is. But it can, double the output of your home garden, right?
Yeah.
Like I put it in my garden bins. It does a beautiful job. Cities buy it to remediate land when they're doing construction, to like prepare roadways and manage water runoff when they're building new roads. So compost is an in-demand product. So community composters and private composters are also springing up because it's a business opportunity. So step one, see if somebody's taking advantage of that business opportunity in your area. Step two, if there is no drop off, you put it in your trash. But the good news is if you put it in your trash and a PLA, PHA goes to a landfill, it is inert. Well-managed landfills are managed not to generate methane. We know that's not always the choice, or that's not always the case with food scraps, but all of these products, they're just going to sit in the landfill and not do anything like everything else in the landfill, because a well-managed landfill, not even the newspapers break down, right? We've all seen the stories of like pulling out the old newspapers. So it's not the ideal end of life scenario. But for some, the fact that they've used a bio-based material in the first place is valuable because PLA compared to the conventional polymers has a carbon footprint about 2/3 less than conventional polymers. And our PHA does as well. So
is that like a cradle to gate or is that cradle to grave?
Field to factory gate. So all of the agriculture feedstock inputs with growing
so
a sugar
like
source.
biogenic sources as well in that. I just want to make sure we're on the same page as far as because LCAs, people can look at them completely different, or PCFs.
Oh yes.
So I just want to make sure that we're aligned on what are our boundaries and how are we factoring it? Because if you are looking at biogenics, I can see how that would be.
So if you include the carbon uptake by the agricultural feedstock source, but you also include all of the inputs, whether it's water, fertilizers, all of that, to be able to produce that agricultural source, and go through manufacturing the polymer. And then when the polymer leaves the gate, that's where I can make that claim. When it comes to converting biopolymers, honestly, in the research that we've done, it's pretty equitable if you average it across the board. Like, it takes roughly the same energy to thermoform a PLA container as a PP one, because these are still fundamentally polyesters. So there's a bit of a wash in the converting step. And then you're right, LCA, when it comes to end of life, is a whole nother story, right? And that's different per region, and that can be hyperlocal. But all that's to say is, if you do put your PLA or your PHA in a landfill, it's not going to hurt anything. You've used a bio-based source, and you use something with a lower carbon footprint. So for when that is important to a brand, a retailer, a consumer, that's kind of its value. Ideally, though, we will build out more and more systems to be able to handle these things. But, the same issue is with, if that was a polypropylene lid, like, it too will just go sit in the landfill.
It's the same situation.
Exactly.
I agree there. It's not what we want. And
No.
even in like traditional polymers, we don't want our products to end up there either. And so it's the same problem, just in a different space. Like,
Absolutely.
Your solution for the end of life isn't necessarily recycling, because that's not what you're building your materials for. You're looking to make compost, which is a great resource, and it is something that we need more of.
Yeah.
For us, we
food
want to
packaging.
reuse it. And if we can reuse it more than once, that makes it great. That's great circular story. Both of these products have circular stories. It's just a completely different image. You're not going package to package. You're going package to growing tomatoes or something like that, which I'm all for, if we could do it more. And in certain parts of the country, do a really great job of collecting this stuff and taking it to the commercial. Because that was always a concern I had, is what do I do here? Because in Charlotte, we do a lot of recycling really well in Charlotte, and we do a lot of collection of trash really well. I never knew what to do with any of the PHA, or not PHA. Yeah, I know what to do with PHA. It goes in the bin in the back. I don't know what to do with the PLA. And
so I looked it up. There are 4 composters in the state of South Carolina last I checked. So yes.
All right.
So there should be a drop-off program.
I use drop-off locations and programs all the time. Here in Mecklenburg County, just north of me, they actually have EPS drop-off, so expanded polystyrene.
Oh, nice.
So whenever I get a package delivered, I throw the EPS in the back of my truck, drive it to Charlotte on my way to take my kids to the mall, drop off the EPS, feel pretty good about life. And so if I can do the same thing with all these PLA lids that I'm getting, great.
I think that's a really important question we have to ask ourselves, is with any of these systems, right? And I think it's equally true for all drop-off programs, is that's a lot of extra labor, right? It's really shifting the burden of dealing with waste to the consumer. And I don't know about you, but I don't have a lot of extra time in most of my days, and I'm super attuned to these issues and hyper aware of all my materials and have more information than the average person to figure out where they should go. But it's a lot of time and effort. And I think that if we're going to make a real impact in terms of collecting and recycling or composting things, we have to have convenient infrastructure, and we have to shift the burden not always onto consumers and try to take it back to a system solution. And that's where conventional polymers have some advantage. It's that with their presence in the market and their scale, it's easy to deploy infrastructure because the material is available. When it comes to biopolymers, that's not necessarily the case. And over the last 20 years, we've seen a bit of a chicken or the egg scenario. Like, do we put compostables out there before the composting infrastructure is available? But what's going to help drive the infrastructure if we're not composting things, right? And kind of that back and forth.
You kind of have to have a critical mass in order to make this thing work. I agree with it.
Yeah.
I have been somewhat critical of PLA in the past. I've had some issues with some materials that I've used in previous jobs. But I'm sure a lot of those things have been resolved by now, because we're talking 10 years ago when I was doing this. What I really am excited about is more the PHA home composter. So the idea to me is if you could get the right kind of moisture and oxygen barrier wrapping your fruits and veggies in a PHA bag or something like that, makes a ton of sense to me. Because then you can just take the whole bag, put it directly into your home composting with all of the waste scraps from like apples or whatever.
Yeah.
And then you can just compost it all right then and there. That seems like a really convenient, great solution if we can get people to compost. And that's another thing. Folks, if you are not composting at home, please do that. It's not hard. It really isn't hard. If I can do it, anybody can do it. Because I literally can't do anything. And I can do that. So please compost. It's a big deal. Anyway,
Yes.
I'm off my soapbox.
I agree. And don't just buy a countertop dehydrator. Like,
oh God, no, that doesn't work. Just get the like the spinny bin on Amazon is like $60. You build it in like 30 minutes, and then you just put stuff in there. You spin it. You add some water. You keep it out in the sun. It works.
Yes.
If I can do it, anybody can do it.
Absolutely.
So PHA.
Yes.
How do we scale? Because I've always seen PHA as almost it's a fringe material now. It's something that I think is growing. And I think there's a lot of applications that it could be useful for. Because I'm a traditional polymers guy, but I don't necessarily think traditional polymers are a good fit for everything that we're using them for. I'm going to say that right now. I think there are certain things that are better suited for other material. And if we can compost it, great. Let's do it.
Yeah.
But how do we scale PHA in a way that it makes sense, where we can really tackle some of these big issues?
Yeah. I think about like the things that go into scaling PHA a lot right now, because, conventional plastics, and with your background, correct me if I have any of it wrong, but I mean, those really scaled and came to market like when natural rubber went into a shortage around World War II. We needed synthetic rubber alternatives,
Metals
right?
And rubber. Yeah.
Exactly. And so coming up with lightweight solutions that would help military applications at that time was a high priority. And afterwards, we were left with competency, capacity, and capability. And we're like, what are we going to do with these plastics? And then you get the invention of saran wrap and Tupperware and like all these different ways to use plastic. But there was this huge initial investment that kind of created that particular industry. And biopolymers coming to market, it's a really different environment. I mean, it wasn't until 2017 that there was really kind of a global flip in how people perceived plastics and became worried about them at the consumer level. And around that time, Europe passed their single-use plastics directive. You had the video of the turtle with the straw up its nose.
Which wasn't a straw, by the way, but
it wasn't a straw.
No, it was a worm. But anyway,
okay. I mean, regardless of what it was, it really galvanized a certain attitude, right, and created very different market conditions for biopolymers to come to market. But scaling them is in a very different place than when conventional polymers came to market. They weren't displacing anything. And to a certain extent, biopolymers have to displace some of the incumbents that we have found. Packaging does really great things for food shelf life, for example. We want to keep doing that. And so biopolymers have to find their way in. So
they have to do the job in the same way, or even better in some cases. Because if you really want to win in this market, because let's be clear, PHA is going to be more expensive than your traditional polymers. So you're going to have either a company that's really committed to composting, like your Whole Foods or people like that, or I would assume would be huge into this, or you're going to have to do something better than the materials that exist today to justify the cost delta. So to me, I think that's the bigger issue, because like the story, I love the story. Let's do more of it. Yes. But then when it comes to the cost of it, I think that's where we're running into a lot of problems. And this is the same issue we're having with recycled materials right now.
Sure.
Just let's be clear. Recycled materials are more expensive than traditional polymers. And because of that, brands don't want to pay it because they say that people don't want to pay more for anything.
Yes.
And I'm assuming you're running into the same kind of conversations. Like, hey, we've got a new widget that solves this problem. It solves end of life for, let's say, food packaging.
Yes.
But it's going to be more expensive.
Exactly.
Are we going to do this?
I know. Yeah. So I think there's a few ways to look at economics, right? As a manufacturer, we think about the economics of our manufacturing, right? And so how can we drive cost out of fermenting PHA, right? And fermenting to make PHA
Why
at
don't we
scale.
talk a little bit about how you make PHA? So then we can talk about the cost structure around that.
Sure.
I think that makes sense because we talk PHA a lot on this so far, and I don't think a lot of people even know what PHA is. So why don't we kind of take a step back on like what is PHA, how is it made, and then that we can transition into why it's going to cost more.
You bet. So PHA, or polyhydroxyalkanoate, it's actually
try to say that all the time. Yeah. I'm so happy you did because I struggle so much with that word.
No problem. I practiced when I joined CJ, right? The PHAs are actually a naturally occurring polymer. So they were, if I recall correctly, first observed in around the 1920s. Scientists observed that little bacteria, for example, would create and store energy in the PHA polymer molecules inside their cellular bodies. But it wasn't till much later and a lot more research that we were able to figure out this is actually a polymer we could make things with. So this occurs like every day out in the world. There are microbes that are making PHA the same way we make fat to store energy. They're making PHA to store and access energy. When we make PHA at scale, we have the ability to encourage those microorganisms to make a lot of PHA, right? And so that's our fermentation process where we take sugars, and you can make PHA from so many different feedstocks. You can use sugars, you can use oil, you can use methane, you can use food scraps. There's a ton of different feedstocks that can be used to encourage microbes to grow a lot of PHA in their cellular bodies. The type of feedstock you choose, its repeatability, its quantity, or its quality can directly affect the type of polymer you create. Because unlike PLA, where if you got PLA from two manufacturers, you can, for the most part, sub them in for each other.
Yeah.
With PHA, there's over 150 different monomers that you can use to create different types of PHAs. So they are not all the same. And there's a lot of different ways you can design PHA for different functional properties. So, and every PHA manufacturer out there has kind of their own special flavor of PHA that they create. You know, for CJ, we have an amorphous and a semi-crystalline version. Other people create different versions of PHVs. Like the alphabet soup can get large when it comes to PHAs.
So the semi-crystalline, sorry to interrupt.
No, it's okay.
What kind of application are you using semi-crystalline in? Because I can imagine, if we're talking just PET, like crystalline PET is going to be used more in like microwave trays and things like that. But then amorphous is going to be in your water bottles. So when I hear those two things, I'm trying to figure out, all right, if you have a semi-crystalline PHA, what is that going into? I'm just curious.
Absolutely. So the semi-crystalline, so the word semi-crystalline and amorphous definitely mean very different things when it comes to PHA properties. So like the amorphous PHA, you don't make anything from it directly. It's really an additive to PLA. You can use it as an additive to other PHA, PVATs. It adds really rubbery ductile properties. It can help PLA compost faster. There's a lot of like cool things you can do, but you don't really use amorphous PHA on its own. Semi-crystalline, you can use on its own or compound with other things. So semi-crystalline is what has been available on the market longer in terms of PHAs. So you can thermoform it, you can compound it with other things to make fibers. So it has somewhat more of a crystalline structure than the amorphous one, but it's probably more similar to PLAs in that regard.
Okay.
But it's not like, It's not the same as like what you would take for crystalline PET to be able to microwave
Yeah,
it, for
I'm
example.
not sticking it in an oven is ultimately what you're
Right.
telling me.
Exactly.
All right.
So
Sorry for interrupting.
no, that's
I was
okay.
just curious.
Absolutely. So there's all these types of PHA that are out there, and when you choose a feedstock, you can get different types of PHA, and that feedstock to fermentation relationship is really important when you're considering economics, right? An accessible feedstock, something that you can access repeatedly, that has repeated quality, is really important for creating high quality PHA. And I think that's where the market struggle has been to a certain degree, is like, how do you match up a feedstock with PHA in a way where your economics can chase down the conventional incumbents? And once you've fed the sugar to those microbes and they've grown PHA in their body, that's when you take them to what we call downstream processing, and you separate the PHA from those cellular bodies. And that process is also really important when it comes to maintaining the quality. So this is a very different process than if you're going to make PLA, which involves, fermentation, yes, to lactic acid, but then a high heat distillation process to be able to get to the polymer. It's very similar to a petrochemical process. PHA is really about how good are you at fermentation and how high quality is the feedstock that you're putting into that fermentation process.
Yeah.
So to a certain degree, it's simpler, but also repeated biological fermentation is not an easy process, and one that's seeing a lot of focus and scale, because we do this for pharmaceuticals. They do that for other industrial ingredients like industrial beer. Industrial fermentation at scale is a really big industry and technology. And so when we're chasing down the economics for PHA, it's going to really focus on that as the manufacturer. But we also think about economics in terms of, right, how fast can you run these materials? Like, line speeds, efficiency in conversion, that's real money. And so we need to work closely with equipment manufacturers, converters, to be able to develop not just a good process, for example, for injection molding PHA, but are there changes to equipment that we can make to be able to run these things at line speeds similar to the incumbents? PLA, having been on the market a lot longer, is starting to see this. Like, Reifenhauser is launching machines for nonwovens with inherent capability to run PLA nonwoven. Bruckner has announced to being able to do PLA biax films with a higher stretch ratio. So these conversion technologies need to scale as much as the manufacturing does to be able to chase down those economics. And then the big question, of course, is end of life. Like, what are we willing to pay for that? It's that as much as we value moisture barrier, where in creating a polymer or a package should the cost for end of life sit? And that's what's kind of spurred the extended producer responsibility discussion and extended producer responsibility legislation. And for good or ill, that's going to factor in a lot when it comes to economics. And right now, it's something that, as we're thinking about scaling, if we wanted to build another factory or something, we need to know what's going to happen with EPR in this country so that we are focusing on applications that are cost advantaged in that system, that we know where biopolymers or compostables have a role to play. And so EPR is trying to look at how do we assign responsibility for the cost of end of life. Because if you wanted to make something from polypropylene today, you do not have an incumbent cost to pay for what happens to it. If it goes to a landfill, that's fine, right? If you buy PHA, you're inherently buying something where end of life is baked in. We've already given you another pathway if you buy a pound of polymer. For polypropylene, that's a little bit different. And so how do we look at valuing inherent biodegradability properties as much as we do moisture barrier or crystallinity or impact strength or something, alongside? And so I think the economics are going to shift what we value, and EPR is kind of focused on helping us do that. So, I mean, nobody wants to build a business solely baked on legislation, because that is tricky and difficult, as I'm sure we are all experiencing in this industry. But the intentions are there to try to balance out those systems, right? And how do we make room for polymers to come to scale? Our plant, we have about 15,000 KTA in our PHA plant. And you compare that to, I don't know, what's an average polypropylene or polystyrene plant? It's like,
A heck of a lot bigger than
billion
that.
tons. Like, it's humongous.
But yeah, the traditional polymer production massively outscales you. No question.
Yeah.
There's
No.
no question about that. I think my main concern about this whole thing is how big of a scale do you think this could actually get to? Do you think PHA just long-term becomes a replacement for a great majority of traditional packaging in plastics? Or do we think it's going to be a niche market because you're going to have certain people that really care about this and certain people that don't? I don't know. I love the idea. I want to see more of it.
Mm-hmm.
I honestly don't see much of it out here. I don't think I've seen PHA straws or lids or anything like that here. I would love it. I'd buy it.
Yeah.
Because then I just throw it directly into my composting.
Yeah.
I'm just curious what your thoughts are.
It's still very new PHA coming to scale. And so probably one of the most visible products made with PHA is food serviceware products under the Fade brand. So if you've ever seen like those marine blue straws and things, like those are made with PHA and probably have the most visibility on the market. But you're right, it is still very new. And I think that's, kind of what everybody's betting on is how big is this going to get? The thing I feel most confident about is that food packaging, if we are really going to get it out of landfills, and frankly, we need compost in this country because we are a huge agricultural country, right? The huge part of what the U.S. is really great at and has land for is agriculture. But also, we have a problem with depleting soils in this country. And
Also true.
we are looking at 50 more years of good harvest based on current soil quality. And it takes millions of years to create new soil. And compost is an incredibly valuable way we can protect our agricultural capabilities in this country. So I think that the pressure to compost food waste will come not just because we want to get it out of landfills, but because we're going to need compost to uphold a really important industry in this country. And with that, I think we can leverage compostable packaging at its best to make it convenient and easy for consumers to get as much food waste as possible and food scraps into compost. And so in that space, I could absolutely see it becoming dominant. And, kind of in the way like you can make a lot of lovely beverage bottles from other things besides PET, for example. It's very technically possible. But having just PET bottles is very helpful when it comes to the recycling stream.
100%
We
agree.
could have a thought like that and this is, out there and will take time. But if we had all of our food packaging be compostable, that helps us make it easy for consumers. You don't have to decide, you're like, this touched food into my compost environment. Our compost infrastructure will grow to be able to run these materials. We'll have capacity for them. Like, that's the part I feel confident about. So when it comes to making PHA at scale, I really see compostable food packaging as really driving like a key part of that industry. I don't know that we're going to be seeing like PHA in cars anytime soon. But like I said, we're still at the very early stages of what we think these polymers can do. A good example on the PLA side, when NatureWorks built the PLA plant and opened it up in 2002, the words 3D printing were not a thing, right?
Yep.
And for the first 10 years of the business, it was not a market to be looked at or related to any sort of quantity. Now we know 3D printing at desktop scale, it's all using PLA. It's a huge market for that material, and we never would have seen it coming, right? It was a whole new thing. And so my question is like, what is the next 3D printing that's out there for PHA and for biopolymers? A really interesting example is PHA is fully miscible in PVC. And it can be a very interesting additive for PVC applications, making it easier to actually recycle PVC. And so we've just kind of been getting started, like talking about that, creating some development projects in the market. But if we could use a biopolymer, not just because it's bio-based or anything, but because it increases the recyclability of PVC, which has unique use cases that we are not prepared to substitute other materials for at this time, that would be incredible. And that could be a huge market. So I think there are some unusual spaces we haven't fully explored or quantified yet for where these biopolymers can go. So,
Yeah. I think
which is
most
why it's so
people,
fun.
if they tuned into this, they would just assume that I would be like, no, we don't want composting because we want plastics. More plastics, please. Like, no, that's not my goal. My goal is to protect my industry, yes. But we don't need to be in everything that we're in. I'm going to say that. I don't care. I don't care if that pisses off everybody in the plastics industry. Sometimes we're making things with our products that we shouldn't do. Somebody sent me a picture once of, I think it was an avocado wrapped in plastic. Like, that's the dumbest thing I've ever seen. And there was a Coke can that was wrapped in plastics. That was the actual dumbest thing I've ever seen. Like, why? It's already in a metal can. There's no reason for that. So there are certain uses that our products are going into that it shouldn't be. And I think that if we have true competition, I'm fine with true competition. I'm not fine with blanket bans that drive us to certain packaging types. I think the free market should work. If your products are better for the application that they're going to go into, by all means, let's use them. Yeah. And I will use them personally because I think composting is the right thing to do. And we need to do more of it. And so I am 100% on board, and I would love to see the success. I do worry about the cost, and I do worry about the ability to scale because it is somewhat of a batch process. And so how do you get that to be big enough where you can actually make an impact? And that's the part that I worry about. And I'd love to stay close to this. And as you guys scale, I'd love to hear more about it and to continue the conversation on how do we make polymers better. It doesn't necessarily need to be fossil-based polymers. It could be any polymers. Yeah. And biopolymers are just that. So
absolutely.
Anyway, I love what you're doing. Yeah. I really hope that it continues to grow. So typically what I do on every episode is I give the guest the ability to talk about anything that we haven't covered, anything that you're really burning on that you really wanted the audience to hear, anything like that. Floor is yours.
There's so many things. That's opening a dangerous door. I've been in this industry a long time. Yeah. So, but just to build off something you just were talking about with, bringing fermentation to scale. I mean, that's one of the reasons that CJ specifically got into this business. Is CJ has a lot of expertise and capability specifically when it comes to fermentation, right? CJ traditionally is not a huge petrochemical plastics company, but what they're great at is fermentation. And so being able to drive the cost out of that process, address those issues with batch fermentation that you were talking about is something that CJ is uniquely positioned to do. And so to have a company of that scale and capability get into the PHA market and see the opportunity, I think is really going to be interesting and help drive it forward, right? This isn't bench scale technology or bench scale labs that we're working with. Like their ability to do fermentation, it crosses pharmaceuticals, food ingredients. They have a huge lysine fermentation plant in Fort Dodge, Iowa. And so
I've seen
I think
it.
that
I've been by there. Yeah.
Excellent. Yeah. So like as companies like this think, what am I good at and what opportunities are out there? I think that that's really going to drive it forward. It's not, square peg, round hole. It's really leveraging things we've done in other industries for biopolymers. So I think that's really going to help address our scale, especially in terms of manufacturing. But one topic we haven't talked about yet, which might be fun, is the topic of microplastics, because it's a complicated topic, right? The idea of identifying microplastics, what is a microplastic? What does persistency mean? What is the impact to human and environmental health? How are we measuring that? I mean, that's starting to play into legislation, and it's a very real topic that we need to address, right? And so I think that, for biopolymers, there's we've seen it kind of go both ways. Like polymers that have inherent biodegradability are not going to be persistent over time. We know that eventually hydrolysis or biodegradability straight from microbial organisms is going to take these polymers apart at a rate that's, decades faster than conventional polymers. But I've also seen the science struggle to be able to appropriately identify materials, what's
Yep.
in them, and what even is a microplastic, and how are we measuring not just presence, but risk and hazard. And so I think that's kind of a wild card for how we're looking at materials right now, because I've seen the science feels a little bit all over the place to me.
Yes.
In some
That
regards.
I could not agree with more. Because I'll see studies that'll say microplastics are killing us. Here's how it's affecting all your health. But then the studies that is referring to usually is this GCM test that showed that there was microplastics in the brain, which actually couldn't tell the difference between plastic and lipid fats. So, like, how much of it was actually microplastics, if any, and what was fat? So, like, there's just, the question is, are microplastics a problem? And I think the answer to that is maybe. I don't think anybody really knows. And I will say right now, with what I've seen, I don't see it as a real danger.
Mhm.
I think it's something as an industry that the plastics industry has to deal with. They're going to have to deal with at least the messaging and the fear mongering. Because right now we're getting just bashed for it. And so we have to deal with that. And I think a company like yours is right there in a pretty prime position. If you're scaling something that is talking about biodegradation, it's a pretty good time to be doing that, because it's just the fear and hysteria. Because I saw there was I hate quoting The Onion, but I'm going to do it because The Onion's not really funny anymore. But said that microplastics, like the 1,000th thing on your list that you should be concerned about today. Yes, it's kind of true, because like, what is it really doing to us, if anything? And I haven't seen anything. And I'll be the first to say, if I do see some sort of concrete link between microplastics and a problem, because I only have one reputation, and I'm not going to just start dying on the hill. If the hill is not worth dying on, I'm not going to die on it. We'll put it that way.
Absolutely. Yeah. It's a tricky question, because
It is.
likewise on the biopolymer side, I've seen newer academic studies that are like, oh, well, are bioplastics even any better, right? In terms of microplastics. And they've done some studies with earthworms or other small organisms, and they're like, oh, we put bioplastics in the soil and the microbiome changed. It's like, but yes, it did, because that's the point of biodegradability.
You added a different material in there. Of course, that's going to happen.
Yes, and nature can respond. Those microbes are going to multiply, and they're going to take it apart, and then the biome will go back. And like, so that is the point of the lack of persistency. But sometimes I think we lose the plot on what we're looking for in terms of these materials. And it's like, you want it to be biodegradable, but you want no actual natural response to these materials if they enter the environment, right? And nobody's trying to design anything that's going to encourage consumers to litter. Nobody thinks that's an end of life path. Nobody advertising like, please litter me because it'll biodegrade.
Yeah, nobody wants that.
It's a backstop. Like, ready biodegradability in the environment for a lot of materials is a backstop, unless it's something that's supposed to be used in the environment, right? Like a biodegradable mulch film or in fishing nets, things like that. Okay. But it's very interesting to see the science on microplastics evolve. And as easy as we may think we have it when we make a biodegradable polymer, there's a lot of fear that we're going to make a regrettable substitution. And the concept of regrettable substitution comes up a lot in the biopolymers space, right?
In California right now, there's a ton of confusion on what's even going to be allowed. I hear nothing but complaints about SB54 and how that applies to compostable packaging. Because I talked to a lot of the packaging companies, and they're worried that it's going to make it so none of these packages are even allowed in there, and unintentionally. I think the law was written so poorly that it's actually going to make some of the solutions to the problems illegal, which makes no sense to me. But that's California. That's what Californians do. They make things more complicated than it needs to be, and they have unintended consequences all over the place. So it's going to be interesting to see how that plays out for plastics and bioplastics and biomaterials and biopolymers. Like how is all of that going to play out? Because you talked about EPR. It's going to be a game changer. And if EPR is done wrong, it's going to cause a lot of problems. California SB54 is EPR done wrong in about every possible way.
Yes.
I applaud them for trying to make a step change and really be aggressive and make things better.
Yeah.
But you've only made things a hell of a lot worse.
Yeah.
That's really where we're at right now.
Absolutely. Yeah, there's a lot of conflict between SB 54 and, the other bill we look at a lot is AB 1201, which is the labeling law related to compostables that was going to make it difficult to sell compostable products there. And that's because, that bill was looking at, it said that to be labeled compostable, you had to be listed on the accepted material list.
On many percentage different.
Under the National Organics Program, right? And so being able to expand the definition of what's allowed in organic compost is an important topic and discussion that we're having right now. And questions around regrettable substitutions is coming up in that debate, right? That's where we're talking about, are these materials safe? There's a lot of questions, rightly or wrongly, about the toxicity of biopolymers, like what could be in them. A common one is biopolymers can't perform. They melt in the heat, they brittle, they break. I mean, you name it. And you have to add crazy additives to be able to make them work. And that is not true these days. And also, we can't add a ton of additive to any biopolymer and make money, because anytime you add something to a polymer, that's increased cost. Nobody is looking to increase cost.
Of course.
Right?
Like we've got 3 additives in my day job in the products that we make. And everybody's like, well, there are thousands of additives in there. It's like, no, we have 3. And the reason why there's 3 is because we don't want it to be more expensive. The hell are you talking about? Thousands. Oh, but to your point of the melting, I saw a LinkedIn post the other day. There was a cup. It was a Starbucks lid that was labeled PLA that had melted. And this guy was going off about PLA. And I was thinking to myself, who knows who the manufacturer of that was? It looked like it was imported. Who knows if it was actually PLA? There's just so many different scenarios here that somebody sees a picture and then they jump to conclusions. That's a problem for biopolymers and traditional virgin polymers and recycled content. That's a problem for everybody, because one image is going to drive this conversation way more. And there was a study recently that I saw that even if you retract a story, once that story gets out there and becomes viral and everybody believes it, it doesn't matter if you retract it. It is now common knowledge, and that is fact. And fighting against that, once that gets out in the world, it's tough. And that's what I'm dealing with every day. And I'm sure you run into the same problems. Like, how do you fight that?
Yes.
It's really hard. It is really hard once there is a negative connotation to whatever to change hearts and minds.
Yep.
But I really, really wish you the best. And I hope that
thank you.
CJ continues to grow in this space and that PHA becomes something that can scale. And PLA too. I don't have a problem with PLA. It's just, I like the idea of the home compostability more. And I would love to see that scale and succeed, because I think that is a huge win for everybody if it does. Sam, I know you haven't talked much on this one, but anything from your end?
No, don't apologize. That was definitely, I think, the most I've learned since I've been on the podcast, to be honest, because I've told Justin many times that like sometimes I get nervous coming in because I'm like, I don't know what you guys are talking about. And I didn't really know what you guys were talking about a lot of the time.
Yeah.
But that's also helpful because I'm learning the entire time. And this is something that I literally knew nothing about. So yes, I was quiet, but I was listening because I just didn't, it's hard to add when you don't know anything.
No, that's okay.
I appreciate your time because this is something that if I wasn't here today, I probably would have never looked into or learned about. So I appreciate you taking the time to talk about it.
And the more you do these, the more you're
the
gonna
more
get
I've noticed
that knowledge base.
Yes.
And then you'll be the one yelling at me to shut up.
Yeah.
Hey, I got stuff to talk about.
Then I'll
which
know
is
everything.
hopefully soon. But
Yeah.
Leah, thank you. And I
thank you.
really appreciate us getting together here. And for Leah and for Sam, Justin Riney, Redefining Plastics, thanks so much. And everybody have a great day. You want to learn more about the plastics industry, recycling, check out these other videos, please like and subscribe.